This is official podcast of Global Eco Trading, an international trading and business consulting company. We conduct trading operations and providing access to exclusive brands of products. Our experience and expertise helps to get high-quality products and reduce our clients' operations costs. We supply not only merchandise, but trust and value. Welcome back to the Deep Dive. Today, we are really zeroing in on one of the most critical, yet, let's face it, frequently botched elements of industrial efficiency.
And that's the health and longevity of rolling element bearings.
Exactly. These are the unsung heroes that, keep everything moving. And when they fail, the cost. It goes so far beyond just replacing a simple part.
It really does.
So our mission today is to extract the essential, actionable knowledge on lubrication, the practices that really make the difference between long life and, well, catastrophic failure. We need the precise answers to maximize bearing life. Okay, let's unpack this.
And we absolutely need to, because the stakes, they just couldn't be higher. You mentioned offshore engineering earlier, and that's a perfect example. Maintenance there isn't just tricky.
It's a logistical nightmare.
It's a total nightmare. I mean, imagine a critical pump bearing failing on some remote oil platform. It's not a $500 part anymore.
No, you're talking about millions in lost production.
Yeah.
Helicopter trips just to get a crew out there.
Exactly. So getting the lubrication right, it isn't just a suggestion. It is operational survival. It's the cheapest insurance policy you can possibly have against the most expensive kind of downtime.
That really puts the problem into sharp relief. And what's fascinating is that most of these failures, they aren't from manufacturing defects or, impossible loads.
No, not at all. They're simple maintenance errors.
Right. And your sources simplify this perfectly, boiling almost all premature bearing failures down to a really simple framework: over, under, or wrong lubrication. Let's start with the absolute biggest one, the one that wastes the most time and money.
That is, without a doubt, over lubrication. It sounds completely counterintuitive, I know.
It does. You'd think more is better.
Everyone thinks more must be better, but the opposite is true. Trying to be overly protective with that grease gun is the #1 cause of early failure.
So tell us about the mechanism there. We hear this term churning in the literature. What is actually happening inside that bearing housing when there's too much grease?
So think of the bearing housing as this tightly packed machine. When you fill all the empty space, the free cavity, too much, the rolling elements are forced to literally plow through a huge excess of grease.
Like trying to run through thick mud.
That's the churning, exactly like stirring thick mud. This action shears the grease, which degrades its structure, but more importantly, it generates massive internal friction.
And that resistance, that friction, is instantly converted into destructive heat.
Instantly. And we're talking about temperatures that can easily exceed the lubricant's safe operating limit.
Wow.
This excess heat, it just deteriorates the seals, it melts them, it warps them, and that allows contaminants to get in later. And it essentially cooks the base oil right out of the grease thickener.
And the pressure.
The internal pressure also forces the seals outward. That's why your most common telltale sign of over-lubrication is visible grease leakage.
So you'll actually see it.
Oh, yeah. Usually followed by a measurable spike in temperature and often a very distinct audible noise from the elements just fighting through all that grease.
Okay, so too much is definitely a problem. But if that's the most common failure, I have to think the opposite problem, under-lubrication, is probably the most destructive.
Absolutely. Insufficient lubrication is almost as bad for longevity if over-lubrication is like a slow cook.
Under-lubrication is an immediate impact.
It's an immediate impact event, yeah. We rely on that
Wear
particles that then circulate through the bearing and just accelerate the wear exponentially. This causes rapid, catastrophic overheating, spalling, total failure.
Now, a quick question that ties back to the technician on the floor. Both over and under lubrication, they present with high temperatures and noise.
They do.
So if a technician uses an infrared gun and sees a high temperature, how can they quickly figure out if it's over or under greased without shutting down the whole system?
That's an excellent practical question. The clue is often in the noise and the pattern of the heat. Over-lubricated bearings, they tend to run hot at first, but they can quiet down a bit as the excess grease gets pushed away.
Okay.
Under-lubricated bearings, on the other hand, they just get louder and hotter the longer they run, and they often show more aggressive vibration because that metal-on-metal contact is so harsh.
So if you see grease leaking everywhere, it's a pretty safe bet.
Safe bet, it's over-lubricated. If it's bone dry and screaming at you, well, you've got your answer.
Which brings us to the third mistake, which you mentioned is the most complex one: using the wrong lubrication.
This is where the nuance really, really matters. It's rarely about using, motor oil instead of grease.
Right, it's more subtle.
It's much more subtle. It's often using two high-quality products that are just chemically incompatible, or using a grease with the wrong viscosity or the wrong thickener for that specific job.
Let's talk about that incompatibility. Most greases use a thickener, sort of like a sponge, to hold the base oil.
Right.
What happens if you mix two incompatible sponges?
The whole matrix collapses. I mean, imagine you have a lithium complex grease and you accidentally mix it with, say, a calcium sulfonate grease. Or even worse, a totally different type, like a polyurea.
Their chemical structures just fight each other.
They fundamentally oppose each other, so instead of a stable gel holding the oil, the mixture turns into this mushy, useless paste that either releases the oil too soon or hardens into a soap.
What's fascinating here is how something so simple, just mixing two seemingly similar products, can cause a total system failure.
It's because the structure that holds the oil, the thing that lets it flow properly under pressure, is just ruined.
So that new mixture, it's not performing as designed at all.
Not even close. So there's simply no guarantee that the viscosity or base type can handle the speeds, the loads, or the temperatures required. The entire protective function is just gone.
So the bearing is effectively running dry, even though there's technically product in there. And what are the telltale signs we'd look for?
Well, beyond the obvious wear and noise, you'll see the grease itself breaking down way too fast. But crucially, the incompatibility often shows up as clogged lubrication paths.
So it creates a blockage.
The thickeners clump up and stop fresh grease from getting to the bearing, which then just makes the whole problem worse by causing localized underlubrication somewhere else.
So the path to failure is now painfully clear. Over, under, or wrong. That's the reactive mindset. Let's pivot to the proactive side. How do we eliminate these errors? How can we actually get bearing lubrication right? Here's where it gets really interesting.
The transition from guesswork to precision, it all starts with the absolute foundation. Following the specs from the original equipment manufacturer, the OEM.
These aren't just suggestions, are they?
No, they are engineering mandates.
Yeah.
They dictate the exact grease type, the precise quantity, and the correct relubrication intervals.
And these parameters, type, quantity, interval, they're based on some pretty sophisticated physics and tribology, right?
Yeah.
What is the OEM calculating?
They're analyzing 5 critical factors. First, bearing size and speed, which engineers combine into what they call the DN value.
Diameter times rotational speed.
Exactly, and that determines the minimum required viscosity. Second, the expected load. Third, temperature, both ambient and operating temp.
Because heat drastically affects viscosity.
It destroys it. Fourth, the environment. Is it dirty, wet, sterile? And then fifth is just the running time. All those factors determine the minimum film thickness you need to prevent metal contact.
That makes perfect sense. And the source material really emphasizes that if a manual is vague, especially about quantity, you can't just guess.
Oh, absolutely not. Eyeballing it is a direct path to over-lubrication. If the manual isn't specific on volume, and a lot of older ones are pretty vague, you have to use the calculation tools.
The ones from the bearing manufacturers.
Yes, they're readily available. They often use a formula that takes the physical dimensions of the its diameters, its width, and applies a correction factor to estimate the precise volume of free space. It takes all the dangerous guesswork out of it.
Okay, so we've nailed the initial spec and volume, but lubrication degrades. We have to talk about reapplication. The source material says this is equally as important as the initial choice.
It is. And scheduling used to be the only game in town. We'd use manufacturer charts, based on speed and temperature, and set a calendar interval, say, every 500 hours. And that's still an excellent starting point.
But not the whole story anymore.
Modern maintenance has moved beyond just following a calendar. If your machine runs cooler than expected, you might be over-lubricating. If it runs hotter or dirtier, you might be under-lubricating long before that scheduled date arrives.
You're talking about the feedback loop, using technology to let the machine tell you what it needs instead of just waiting for a date on a schedule.
Precisely. We now use predictive maintenance to determine the need for lubrication in real time, often before any damage is done.
Like ultrasound.
Take ultrasound, for instance. It listens for high-frequency sounds from friction, that microscopic rubbing we talked about. A technician can listen to a bearing and hear this distinct high-frequency chatter that says it's starved for grease.
And they can lubricate it right then and there.
They can lubricate it just until that sound level drops back to baseline. It ensures they add exactly the right amount. It prevents both under and over lubrication at the same time.
That's a huge step forward. It addresses both extremes in one go.
What about vibration analysis and thermography? How do they fit in? Vibration analysis is a bit more complex. It's fantastic at detecting physical damage, but changes in lubrication can also shift the overall vibration baseline. A bearing running dry will often show increased overall vibration.
And thermography is the quick check.
It's the quickest check. Since heat is the universal symptom of friction, whether it's from too much grease or metal on metal using infrared cameras is a fast, non-contact way to spot components in distress. Anything running hotter than its peers is screaming for a mention.
And finally, you mentioned just simple visual checks,
Meh.
like the color of the grease.
Yes, don't overlook the basics. If the grease turns black, that could be carbonizing from extreme heat. If it looks muddy, that's contamination. And of course, the actual application method matters.
Using clean equipment.
Dedicated clean equipment. If you pump clean grease into a fitting that's caked in mud, you've just contaminated the entire system right at the source.
This has been incredibly insightful. So what does this all mean for you, the listener, who's in charge of maximizing component life and cutting costs?
Yeah.
We've learned that avoiding the over-under wrong mistakes is a deliberate strategy.
It is. It's a multi-layered one.
It means shifting from guesswork to a proactive, data-driven approach. It's rooted in OEM specs, precise calculations, and real-time monitoring.
And that shift is paramount. This knowledge isn't theoretical. It's a direct shortcut to operational efficiency and achieving that goal of reducing clients' operations costs that we mentioned at the start.
By extending component life and eliminating that unexpected expensive downtime, you really do improve the bottom line.
If we connect this to the bigger picture, the difference between a world-class maintenance team and a struggling one, it often comes down to recognizing those subtle early signs.
That faint, high-frequency sound on an ultrasound device.
Or the slight temperature variance on a thermograph. That's the difference between a simple 5-minute relube and a catastrophic breakdown that stops production entirely. So it raises an important question for you. Is your organization just relying on outdated schedules, or are you using the available technology to really inform your lubrication needs?
That is the essential question. Maintenance inertia versus technological adoption. But let's end with a thought on the human element, because standards are only half the battle. If following OEM specs is the baseline, what do you think is the single greatest reason a maintenance team ignores them in the field, leading to those over, under, or wrong failures? Is it time pressure, inventory complexity, or just that ingrained belief that more is better? Something to consider as you review your own processes. Thank you for joining us. This was the Global Eco Trading Podcast. Subscribe so you don't miss upcoming episodes covering the latest business news. See you in the next episode.